everybody. Good morning. Myself, Dr. Shubhankar Sen, an Associate Professor in the Department of Mechanical Engineering, IIT ISM Dhanbad, welcome you to the first lecture of the fifth module of the 12-week SWAYAM NPTEL course, Finite Element Method in Thermal Engineering. In today's class, we shall illustrate the implementation of boundary conditions in conjunction with heat conduction problems in 1 dimension and 2 dimensions. In the previous weeks, we have already considered some cases of convective, radiative, essential as well as natural boundary conditions in conjunction with heat conduction problem, mostly in 1 dimensions, and for EBC, we have also shown in 2 dimensions. So, for a heat conduction problem, we encounter 4 types of boundary conditions. The boundary conditions are EBC, NBC, CBC and RBC. So EBC is essential or Dirichlet or displacement boundary condition. NBC is the natural or flux type boundary condition. CBC is the convective boundary condition, and RBC is the radiative type boundary condition. So we shall illustrate the implementation of boundary conditions in 1 dimension and 2 dimensions. So let us begin with the essential boundary condition. So first we consider implementation of EBC. We already mentioned that this EBC and NBC, they alter only the load vector at the element level. They do not modify the element level stiffness matrix, whereas RBC and CBC, they augment the element level stiffness matrix and upgrade the element level load vector. So CBC and RBC both augment KE and FE. In contrast, EBC and NBC only update the FE. So this is a contrasting feature with respect to the EBC NBC set and the CBC RBC set. Implementation of boundary conditions amounts to alter the load vector. The nodes at which EBC, NBC, CBC and RBC are specified, the DOF is unknown at such nodes. For heat transfer problem, the DOF is temperature capital T. Since the heat transfer equations are of second order, we can have a maximum boundary condition of order 1, and because of that we cannot use 2 boundary conditions at the same node. So we can use only 1 type of boundary condition at a given location. So as I have already written here, that at the essential boundary, temperature is given at the remaining 3 boundaries. We know the prescribed quantities for heat flux, but we do not know the temperature. So we write the element level equation at those nodes where temperature is unknown at the boundary points. So let us consider a two-dimensional domain. So this portion, the right side boundary, is subjected to essential boundary conditions. So this is omega. Now we consider part of the boundary is having elements of triangular type and one element I am showing as quadrilateral type. So we shall use the essential boundary conditions here. So let us consider the elements are, this is, let us take as element P, this is element Q, this is element R, this is element S, and this is element small t. So these are the element numbers. Now for the triangular element, we have local node numbers in this fashion, 1, 2, 3. We can also use for this kind of orientation 1, 2, 3. All these have been discussed in our previous classes. For the quadrilateral element, our local node numbering is 1, 2, 3, 4 in the anti-clockwise manner. Now let us consider T equals to Tg at the right boundary. Right boundary. So this is our x-axis. This is the y-axis. So this is gamma g, and this total boundary is gamma. Okay. So now let us redraw this picture here. So at the right boundary, we have elements. So we have triangular elements and one quadrilateral element. So here our temperature is given as Tg, 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 Tg at the boundary. So this is gamma g, the right boundary. So this is element number P, element Q, element R, element S, and element T. So these are element numbers. So we again show the local node numbering here. 1, 2, 3. 1, 2, 3. And here we have 1, 2, 3, 4. The local or elemental node numbering have been specified. Now let us consider the element level matrix equation system. Ke Te equals to Fe or Kije Tje equals to Fie. For the quadrilateral element of bilinear type, we have nodes 1, 2, 3 and 4. This is element T. Our unknown temperatures are T1T, T2T, T3T, and here T4T. So this element level matrix equation, we can write it as K11T, K12T, K13T, K14T, K21T, K22T, K23T, K24T, K31T, K32T, K33T, K34T, K41T, K42T, K43T, and finally K44T. So this is the element level matrix equation system for the quadrilateral element. The unknown temperatures are T1T, T2T, T3T, T4T equals to F1T, F2T, F3T, and F4T. So this F1, F2, F3, F4T, they come from the source term. So KE equals to FE, where E equals to T, gives this matrix equation system. So this is KT, this is TT, and this is FT. Okay, now for this particular element, this is our part of the gamma G, T2T and T3T are already given. This implies that T2T equals to Tg and T3T equals to Tg. Therefore, we do not require algebraic equations at local nodes 2 and 3 of element T, since nodes 2 and 3 belong to eta G, the set of essential boundary nodes eta G. So these equations 2 and 3 at the local level, they don't exist. We have to write the equations only at local nodes 1 and 4, that are the internal nodes. So these two equations, they become redundant or they degenerate. Okay, so the above 4 by 4 matrix equation system simplifies to K11 T T1T plus K12T T2T plus K13T T3T plus K14T T4T equals to F1T and K 41t T1t plus K 42t T2t plus K 433 T3t plus K 44t T4t equals to F4t. These are algebraic equations at unknown nodes of element T. Now T2t equals to Tg and T3t equals to Tg given on gamma g, and all the known terms are shifted to the right hand side load vector. So the above equations may be rearranged as K11t T1t plus K14t T4t equals to F1t minus K12t T2t minus K13t T3t, and the second equation is K41t T1t plus K44t T4t equals to F4t minus K42t T2t minus K43t T3t. Okay, so these equations we can rearrange as the matrix form: K11, K14, K41, K44, T1t, T4t equals to F1t minus K12t T2t minus K13t T3t. In the second row we get F4t minus K42t T2t minus K43t T3t. So this is 2 by 1, 2 by 2, 2 by 1. Now this portion, this is the EBC contribution, and this is contribution from the source term. Therefore, implementing EBC amounts to modification of the entries of element level load vector of unknown temperature. So the right hand side vector, which we can represent it as F IT equals to F, this we can give tilde, F I tilde T equals to F IT minus summation of K I B T TB T, where B belongs to eta G. I, local node of element T at which algebraic equation is written. B equals to EBC node of element T. So, when I equals to 1, B is varying from 2 and 3. So, we are getting K12E, K12T and K13T. When I equals to 4, similarly B must have the same values. B equals to 2, 3, the same values we get. So from this expression we have generalized the boundary condition formula for the specified temperature boundary condition. This we have already illustrated in the previous weeks in terms of examples, and derivation we have shown in today's class. So we rewrite this expression Fi tilde equals to Fit minus summation of Kibt Tbt, where B belongs to eta G. This is applicable only for elements whose nodes reside on gamma G. So this is the EBC contribution. This is contribution from the source term. Now, if we go back to the sketch with which we started our problem, so this is the triangular elements we are showing. This is element P, element Q, element R, element S, element T. So here we have T given, T given, T given, T given. This is gamma G, and we have shown the element local node numbering 1, 2, 3, 1, 2, 3, and for the quadrilateral we already showed it. This is 1, 2, 3 and 4. Now we can use this formula developed for the implementation of EBC for individual elements. For the linear triangular element P, we have F1P equals to F1P tilde equals to F1P minus K12P T2P minus K13P T3P. Now T2P and T3P, they are equal to Tg, the given temperature. So we can write it as F1P minus K12P Tg minus K13P Tg. So this is for element P. Now if we go for element Q, for element Q of linear triangular type, we have local node 2 on the boundary. Therefore, F1E and F3E will be upgraded. So for this case, F1 tilde Q equals to F1 Q minus K 1 to Q T2Q equals to F1Q minus K1 to Q into TG, and then we have F3 tilde Q equals to F3Q minus K32Q T2Q equals to F3Q minus K32Q TG. So in the same way, we can show the element contribution for element R. So we show it for the linear triangular element R. We can similarly have F1 tilde R equals to F1 R minus K1 to R T2R minus K13 R T3R equals to F1R minus K12R TG minus K13R TG. Now, so this illustrates the implementation of essential boundary condition in 2 dimensions. This concept we can show now for 1 dimension. Now, illustrate the implementation of EBC in 1 dimension. So let us consider a boundary element E with local nodes 1 and 2. At the rightmost node, temperature is given as Tg given. In this case, temperature is unknown at the local node 1, or T1E is the unknown quantity and T2E is the given quantity. So we have to find out F1E. So F1E tilde will be F1E due to source term minus K12E T2E. This is for 2 noded bar elements. Now let us consider a cubic or 4 noded bar element whose one node belongs to an essential boundary. So this is the cubic element. It has 4 local nodes, local node 1, 2, 3 and 4. This is element E and this is delta x. This is the x direction. So this point belongs to gamma g. So T4E equals to Tg, the given temperature. Implementation of EBC amounts to upgrade the load vector components at local nodes 1, 2 and 3. We know that FIE equals to FIE tilde equals to FIE minus summation of K IBE TBE B belongs to eta G. Since we have only one node at the boundary, here B equals to 4. The above expression simplifies to FIE tilde equals to FIE minus K I4E T4E, where I is varying from 1 to 3 only for the unknown nodes. At node 1, the temperature is T1E, at node 2 it is T2E, at node 3 it is T3E, and at node 4 it is T4E. So T1E, T2E and T3E are unknown temperatures. So for I equals to 1, we get F1E tilde equals to F1E minus K14E T4E equals to F1E minus K14E into Tg. For I equals to 2, F2E tilde equals to F2E minus K24E T4E equals to F2E minus K24E into Tg. And finally, for I equals to 3, F3 tilde E equals to F3E minus K34E T4E equals to F3E minus K34E Tg. So we have illustrated the implementation of the essential boundary conditions in one dimension and in two dimensions. In one dimension, we have considered the two-noded bar element, and also we have considered a four-noded or a cubic bar element. In two dimensions, we have considered linear triangular as well as bilinear quadrilateral elements. We have derived a generalized formula for implementation of the boundary conditions. Now we illustrate the implementation of the natural boundary conditions. Consider implementation of natural boundary condition. Okay, so let us consider that the square domain in two dimensions, the right boundary, this is gamma h. So here Q0R is given. So we consider a bilinear quadrilateral element on this boundary. So this element is element E. Its local nodes are 1, 2, 3 and 4. So this is the x-axis, this is the y-axis, y, this is x, this is omega, and the governing equation we can take as the Poisson's equation, k del square t plus q equals to 0 as the model equation. Now at the right boundary, our Q0R is prescribed heat flux. So Q0R is specified as NBC data on gamma H. Now we have already derived the weak form in a compact form of the heat conduction equation subject to all four types of boundary conditions. In that case, our NBC contribution, it was shown as FIE equals to FIE source plus FIE due to NBC. So it was Q into integration over omega E psi IE d omega E plus integration over gamma E psi IE into K del T del N into d gamma E. So this is the expression. So this portion, it amounts to the NBC part, and the first part contributes to the source term. Now this heat flux, it is specified along the boundary 2, 3, and it does not have any contribution along the remaining edges. So specified heat flux Q0R acts only along the edge 2, 3 and does not have any counterpart along the edges 1, 2, 3, 4 and 4, 1. Fluxes for the internal edges are balanced by fluxes of the neighboring elements. Therefore, the boundary integral term integration over gamma E psi IE K del T del N d gamma E, it can be split into simple line integrals along the edges of the element E. So we can write it as integration along 1 to psi IE K del T del N d gamma E plus integration along 2, 3 psi IE K del T del N d gamma E plus integration along 3, 4 psi IE K del T del N d gamma E plus integration along 4, 1 psi IE K del T del N d gamma E. Now, the internal edges have no contribution to the Neumann boundary condition or the natural boundary condition. Because of this, the first integral, the third integral and the fourth integral, they disappear, and this expression integration along the boundary psi IE K del T del N d gamma E, it reduces to integration along the path 2 to 3 psi IE K del T del N d gamma E. It means that the four-noded quadrilateral element, it effectively reduces to a two-noded bar element. It means that, therefore, in relation to implementation of NBC, the four-noded quadrilateral element E reduces to a two-noded or linear bar element. So we can show this here as this is the gamma H boundary. So our element, it was local nodes 1, 2, 3, 4, element E. So this was Q0R. The mesh size, this is delta Y along the Y direction and delta X along the X direction. So this becomes equivalent to a two-noded bar elements with local nodes 2 and 3. Here this heat flux is specified as Q0R, and this is the boundary gamma H, and the mesh size is delta Y. Therefore, the load vector for element E is given by FIE tilde equals to FIE plus integration along 2, 3 psi IE into K del T del N d gamma E. So this is the NBC contribution. So let us deal with the NBC contribution. Integration along 2 to 3 psi IE K del T del N d gamma E. So this is FIE NBC. So this gives us FIE NBC contribution. Now we know that this K del T del N term, it gives us the Q0R contribution, the specified heat flux. So this can be written as integration along path 2, 3 psi IE Q0R d gamma E. Now Q0R, this is a constant, it comes out. So Q0R integration from 2 to 3 psi IE d gamma E. Now we perform this integration using the natural coordinate system. So this we take as Q0R. Then this integration limit, it changes from -1 to 1. Then psi IE is represented in terms of eta and d gamma equals to dy. So d gamma E equals to dy equals to determinant of the Jacobian matrix into d eta. So determinant of the Jacobian matrix is delta Y by 2 into d eta. So this gives us delta Y by 2 into d eta. So we can simplify FIE NBC equals to Q0R into delta Y by 2 integration from -1 to 1 psi IE d eta. For I equals to 1, F1E NBC equals to Q0R delta Y by 2 integration -1 to 1 psi 1E eta d eta equals to Q0R delta Y by 2 integration -1 to 1 half of 1 minus eta d eta equals to Q0R delta Y by 4 into eta minus eta square by 2 the limit is -1 to 1. This we can simplify as Q0R delta y by 4, 1 minus half minus -1 minus half equals to Q0R into delta y by 4 into 1 minus half plus 1 plus half. So this gives us Q0R delta y by 4 into 2 equals to Q0R into delta y by 2. So for I equals to 2, F2E NBC equals to Q0R delta y by 2 integration -1 to 1 psi 2e eta. So psi 2e eta is half of 1 plus eta d eta equals to Q0R delta y by 4 eta plus eta square by 2 from -1 to 1. This is given as Q0R delta y by 4 1 plus half minus -1 plus half equals to Q0R delta y by 4 into 2 equals to Q0R delta y by 2. Therefore, we can see that the NBC contribution is equally shared by the two nodes. Therefore, FE NBC equals to Q0R delta y by 2 1 by 1. So, for the boundary node, therefore, for the boundary element E, the load vector at nodes 2 and 3 construct Fe tilde 2 by 1 equals to F1E, F2E from the source term plus Q0 delta y by 2 into 1, 1. Now I redraw the picture. This is node 2, this is node 3, this is the mesh size delta y, this is the natural boundary gamma h. So this is T2E, this is T3E, this is for element E. So T2E and T3E are unknowns at the natural boundary. Now let us go for the physical interpretation of this expression. If we consider heat flux Q0R specified and we have a bar element with size delta y, the nodes of the bar elements are 2 and 3. The heat Q0R into delta y is equally shared by nodes 2 and 3 of the bar element E. Therefore, for two noded or linear bar element F2e equals to half of Q0R delta y equals to Q0R delta y by 2, and F3e, it also shares the remaining half into Q0R delta y equals to Q0R delta y by 2. This relationship of equal share is, however, valid only for the two-noded or linear bar elements and not for the three-noded or even higher order bar elements. Therefore, for a quadratic or serendipity boundary quadrilateral element, the heat will not be shared in an 1:1 ratio. The ratio will be 1:4:1. So this is a very important observation. This we should note it. So I highlight this portion. Let us consider a quadrilateral element at the boundary, gamma Neumann. So this is gamma Neumann, and we have this element E. So local nodes 1, 2, 3, 4, 5, 6, 7, 8, 9. So this node numbering here, I did not follow counterclockwise node numbering. I have given this numbering without any convention. So this is only for illustration purpose. Okay. So for NBC implementation, the quadrilateral will reduce to a three-noded or quadratic bar element. So I show the sketch here once more. So this is our gamma edge. So now the local nodes are 3, 6 and 9. So element has reduced to a quadratic bar element. The other nodes were 1, 2, 4. At the center we had node 5. At the top boundary we had nodes 7 and 8. So we have finally the element as local nodes 3, 6 and 9. Our heat flux is Q0R. Q0R, this is given. So Q0R is specified. So this dimension is delta Y, the mesh size, and this is the gamma H. We can consider this as the Y direction. Okay, so this is delta Y and this dimension is delta X. So this local node 3, it is equivalent to local node 1, local node 6 is equivalent to local node 2, and local node 9 is equivalent to local node 3. Now we know that for a quadratic bar element, psi 1 is xi equals to minus xi by 2 into 1 minus xi equals to minus xi by 2 plus xi square by 2. Psi 2 is xi equals to 1 minus xi square and psi 3 is xi equals to xi by 2 into 1 plus xi. So this is xi by 2 plus xi square by 2. Now we know that FIE NBC equals to Q0R integration minus 1 to 1 psi IE d gamma E equals to Q0R integration minus 1 to 1 psi IE eta d gamma E is dy. This is determinant of the Jacobian matrix into d eta. So determinant of the Jacobian matrix is delta y by 2 into d eta. This we can write as Q0R into delta y by 2 integration minus 1 to 1 psi IE eta d eta. For I equals to 1, F1E NBC equals to Q0R delta y by 2 integration minus 1 to 1 psi 1 E eta d eta equals to Q0R delta y by 2 integration minus 1 to 1 psi 1 E eta equals to minus eta by 2 plus eta square by 2 d eta equals to Q0R delta y by 2 minus eta square by 4 plus eta cube by 6 from minus 1 to 1 equals to Q0R delta y by 2 minus 1 by 4 plus 1 by 6 minus 1 by 4 minus 1 by 6 equals to Q0R delta y by 2 into minus 1 by 4 plus 1 by 6 plus 1 by 4 plus 1 by 6. This gives us Q0R delta y by 2 into 2 by 6. So this is Q0R delta y by 6. Now, if we consider I equals to 2, then we have F2E along the natural boundary equals to Q0R delta y by 2 integration minus 1 to 1 psi 2e eta d eta equals to Q0R delta y by 2 integration minus 1 to 1 minus eta square d eta equals to Q0R delta y by 2 eta minus eta cube by 3 minus 1 to 1. This gives us Q0R delta y by 2 1 minus 1/3 minus 1 plus 1/3. So this gives us Q0R delta y by 2 into 1 plus 1, this is 2 minus 2 by 3. This is equals to Q0R delta y by 2 into 2 minus 2 by 3 equals to Q0R this gives us F2E NBC equals to Q0R delta y by 2 into 2 minus 2/3 equals to Q0R delta y by 2 into 4 by 3 equals to Q0R delta y into 4 by 6 equals to 4 by 6 Q0R delta y. Since the overall heat is Q0R into delta y, it gives us F3E NBC equals to Q0R into delta y minus F1E plus F2E NBC equals to Q0R delta y minus Q0R delta y into 1 by 6 plus 4 by 6 equals to Q0R delta y into 1 by 6. By calculating F3E NBC equals to Q0R integration minus 1 to 1 psi 3 eta delta y by 2 d eta equals to Q0R delta y by 2 integration minus 1 to 1 eta by 2 plus eta square by 2 d eta. It can be shown that this expression will be Q0R delta y by 6. Therefore, the heat at the nodes of a quadratic bar element is not shared by 1:1:1 ratio, but by 1:4:1 ratio. Now consider triangular element at the boundary. Gamma h. So this is gamma h. So we have triangular elements of this type. This is element P, element Q, this is element R, this is element S, and the heat flux specified is Q0R. So local node numbering we have already shown here. 1, 2, 3, 1, 2, 3. This is the local node numbering for contrasting orientation of the triangular element. For element P, F2P equals to Q0R into delta Y by 2. F3P equals to Q0R into delta Y by P. So this dimension is delta Y. This dimension is also delta Y, because the edges of the triangular element, they also act as two-noded bar elements. Edges of the linear triangular element also act as two-noded or linear bar elements. Then entire heat Q0R, it is taken by the second local node of element Q. So F2Q equals to Q0R, because it has only one node at the boundary, and entire heat added to that boundary is taken by this particular node. So there is no share of heat flux. Then let us consider for the third element. This is for element Q. For element R, we have F2R equals to Q0R delta Y by 2, and F3R equals to same contribution delta Y by 2. Now this common node at the boundary for elements P, Q and R, we denote by the global node M, global node. So F M, the load vector at node M for NBC contribution, this will be F3P plus F2Q plus F2R. Now F3P equals to Q0R into delta Y by 2, F2Q equals to Q0R, and F2R, this is Q0R delta Y divided by 2. So we get here Q0R delta Y 2 times, so it is added and we have another Q0R. So this is Q0R into delta Y plus Q0R. So this should be certainly 2. Let us consider NBC in one dimension. So this is the NBC end of a rod. So here x equals to 1. This is x axis. This is x equals to 0. So here Q0R is specified. So let us consider a boundary element. This is element E, local node 1, local node 2. This is Q0R. So this is T1E. This is T2E. Q0R is specified. T1E and T2E are both unknowns. Now F2E tilde equals to F2E source plus boundary integration over gamma E psi IE K dt dx d gamma E. This is for one dimension. So this is F2E source plus integration over gamma E psi IE Q0R d gamma E equals to F2E source plus Q0R is a constant, integration over gamma E psi IE d gamma E. Here I equals to 2. So this gives us F2E source plus Q0R integration over gamma E psi 2E d gamma E. Now the local node 2 of element E acts as a single noded point element. For this element, there is only a single shape function, and this shape function must have a value of 1, since summation of psi I equals to 1, where I is varying from any n. Psi 2e equals to 1 for a single noded point element. So this reduces to F2E tilde equals to F2E source plus Q0R into boundary integral of d gamma E. Now this term must be unity because the entire heat is taken by local node 2 of element E. So this gives us F2E tilde equals to F2E source plus Q0R. Now, if we have a quadratic bar element for the NBC problem, in that case, we have Q0R given, this is T1E, T2E, T3E, this is element E, this is delta X. Now, the heat flux at local node 2 does not affect the boundary condition or the load vector for local nodes 1 and 2. NBC at local node 3 of a quadratic bar element does not affect the load vector at nodes 1 and 2. Therefore, F1E tilde equals to F1E source, F2E tilde equals to F2E source, and F3E tilde equals to F3E source plus Q0R. So this we should note. So this is for quadratic bar element. Now we conclude today's class here. We have illustrated the implementation of EBC as well as NBC in 1 and 2 dimensions. Both of EBC and NBC update the element level load vector Fe, but do not influence the element level stiffness matrix or the K matrix. The NBC reduces a quadrilateral or triangular element at a boundary to effectively a bar element in relation to implementation of EBC. In the second lecture of this week, we shall illustrate the implementation of convective as well as radiative boundary conditions. For today's class, I suggest the textbooks authored by Professor T.J.R. Hughes as well as Professor J.N. Reddy. Thank you very much for attending today's lecture.